Distribution. Approximating the binomial when n is large and p is small. Suppose a random variable x has a binomial distribution. Assume n is very large and p is small. So for example, n may be 50 or 100 and p 0.01 or smaller. Let's define a parameter mu equals n times p. We're interested in what happens when n grows and p gets smaller. So let's define p to be mu divided by n, where mu is some fixed constant. In other words, n times p remains constant as n grows. Parameter mu has a meaning for the binomial. For example, if I have 1,000 trials and the probability of success on each trial is 0.01, 1 in 100, then mu is 10. It's the number of successes you might expect on 1,000 trials, the average number of successes. We'll refer to it later as the expected number. Let's compute the probability x equals 0 for a binomial. This is the probability that all n trials result in a failure, 1 minus p to the power n. But remember, p is some constant mu divided by n. So we have 1 minus mu over n raised to the power n. And you might recognize this as a quantity which converges to an exponential. In fact, as n goes to infinity, it converges to e to the minus mu. This you will have seen in a calculus class. What about the probability that x equals 1? For the binomial, this is n times p times 1 minus p to the n minus 1. I'd like to use the convergence of the probability x equals 0, so I rewrite this as np divided by 1 minus p times 1 minus p to the power n. Because I know what happens to 1 minus p to the power n as n goes to infinity, it converges to e to the minus mu. On the other hand, as n goes to infinity, n times p is equal to mu, and 1 minus p in the denominator converges to 1 because p goes to 0. So the probability x equals 1 converges to mu times e to the minus mu. We can similarly work with the probability x equals 2 and show that that converges to mu squared over 2 e to the minus mu. Or in general, for any value of x, probability x equals little x converges to mu to the x over x factorial e to the minus mu, x equals 0, 1, 2, and so on. This convergence occurring as n goes to infinity and p equals mu over n converging to 0. It turns out we've discovered the probability function of one of the most famous discrete distributions of all, called the Poisson distribution, after French mathematician Poisson. The Poisson distribution represents a count, or the number of events of some type. Let's suppose that the rate of these occurring is denoted with the Greek letter mu, some positive parameter. Then we say a random variable x has the Poisson distribution if the probability function for x is given by f of x equals mu to the power x e to the minus mu divided by x factorial. And since it's a count, x could be 0, 1, 2, it could be any non-negative integer. In this case, we'll write x is distributed according to the Poisson with parameter mu. One of the first things we should do is check that this is indeed a legitimate probability function. It's obviously a non-negative quantity, but do the values of f of x add to 1? The sum, as x goes from 0 to infinity, of f of x is the sum of mu to the x e to the minus mu divided by x factorial. We can take e to the minus mu, a constant, outside that summation, and we're left with the sum of mu to the power x divided by x factorial. You might recognize that as the series expansion of the exponential e to the mu. It's the Taylor series expansion of e to the mu. So we obtain e to the minus mu times e to the mu, and the product of those two, of course, is 1. In general, the Poisson distribution, Poisson models, are used for problems involving counts. For example, the number of phone calls to a call center in a period of time, a 1-hour period, say. The number of new connections to a wireless network or a printer in 1 unit of time. The number of cases of a disease which are, say, non-contagious in a given region or a town. The number of vehicle accidents per day or month in a town covered by a specific insurer. The number of cars on a highway that pass a given point per hour if we ignore rush hour effects, for example, when the density tends to be higher. Here's an example. Calls to a call center. Suppose the average number of calls to a call center in an hour is 8. Find the probability that in a given hour, there are at least 3 calls. The random variable of interest here, let's call it x, is the number of calls in a 1-hour period. X follows a Poisson distribution, and we're told what the parameter is. Mu is equal to 8 in this case. So the probability function is e to the minus mu, e to the minus 8, 8 to the power x over x factorial, again as x goes from 0, 1, 2 through the non-negative integers. We're asked to find the probability there are at least 3 calls. In other words, the probability that x is greater than or equal to 3. We could obtain that by computing the probability of the complement and subtracting from 1. 1 minus the probability x is less than or equal to 2, which is 1 minus f of 0 minus f of 1 minus f of 2. So if we now put in the probability function f of x, this becomes 1 minus e to the minus 8, minus 8 e to the minus 8, minus 8 squared e to the minus 8 divided by 2. Numerically, that turns out to be 0.9862, so there's a very high probability that x is greater than or equal to 3. Essentially what we've seen is that the Poisson distribution can be used to approximate the binomial. We've seen that if we have a random variable x, which is binomial with parameters n and p, and if the number of trials goes to infinity, and the probability of success goes to 0, with mu equals n times p remaining constant, then the probability that x equals little x converges to the corresponding probability for a Poisson random variable, mu to the power x e to the minus mu over x factorial. In other words, if we have a very large value of n and a small value of p, we can use the Poisson distribution, with mu defined by n times p, as an approximation to the binomial. This will avoid the sometimes difficult calculations for the binomial of n choose x, when n and x are both large. Once again, the theorem states that as n goes to infinity and mu remains constant, p equals mu over n, and if x is a binomial with parameters n and p, then the probability function for the binomial converges to that of the Poisson, mu to the x, e to the minus mu over x factorial. Here's an example involving the incidence of childhood leukemia in a town in Illinois. It was observed during a 5 1/3 year period, from 56 to 61, in a small town called Niles, Illinois, a town in Cook County near Chicago, that there seemed to be a higher incidence of childhood leukemia. Indeed, there were 7,076 children of appropriate age that were at risk, and there were 8 cases reported over this period of time. On the other hand, if we used the rate of childhood leukemia reported in the rest of Cook County, excepting the town of Niles, over this period of time, we would have forecast that a community of this size, over a similar period, 5 1/3 years, would have an expected number of around 1.75 cases of childhood leukemia. So the question is the higher value reported in Niles significant? Is it too high to be explainable by random chance? What we're looking to do, then, is to compute the probability that x is greater than or equal to 8 on the assumption that x has a Poisson distribution with parameter mu equals 1.75. And if that probability is extremely small, we'll conclude that it's unlikely this happened by chance. The solution. Well, to begin with, we assume the rate in Niles is the same as the rest of the county. Indeed, we're essentially approximating a binomial random variable in which the number of trials is 7,076, and the probability of leukemia is p equals 1.75 divided by n. Here n is large, p is small, and so it's an appropriate problem in which to use the Poisson approximation to the binomial. Then the probability that x is greater than or equal to 8 is the sum of the probability function from 8 to infinity, which can also be obtained by subtracting from 1 the sum as x goes from 0 up to 7, 1.75 to the power x, e to the minus 1.75 divided by x factorial. This indeed numerically works out to a pretty small number, 0.00047. It's an event that would occur at random only one time in approximately 2,000 trials. It's a very small probability, it's very unlikely to happen by chance, so it appears to indicate that the assumption that the rate in Niles was the same as the rest of the county, 1.75, is wrong, and in fact is probably considerably higher.